Hi, thank you for taking the time to be here, to listen to the presentation. In this afternoon, we will be discussing about OSED, this is the open source EDGE DERMS. Everyone knows what is a DERMS, knows what a DERMS is, no? Is demand energy renewable management system, DERMS, how I forget? Distributed energy renewable management system, I think it is. Yeah, distributed energy renewable energy management system. So it will be me speaking with Rodrigues. I will be brief in the presentation. We will just go for a little bit of introduction, which is the context that why we did this, what is the platform itself, what we can do with this, and which is the future vision. So who are we? We are a part of the research center of Hydro-Québec. Myself, architect, software architect, solution architect from Hydro-Québec, and there is a team of developers that help the scientists, that help our work, and he's the manager. So we have the scientists and developers that contribute to the scientific job. Hydro-Québec is a vertical integrated utility. We don't have markets, internal markets per se. The residential electricity rates are among the cheapest in North America for the residential sector. The other sectors are competitive. We have a unique and proprietary aggregator, so the utility itself owns the aggregator. More than 95% of renewable energy already, everything comes from hydro. And the few percentage that is left is the regions in the north that relied on diesel. But because they are not interconnected to the system. We have 63 hydroelectric power stations. And just for comparison of how big it is the biggest producer of electricity in Canada. So Quebec produces 37 gigawatts of power and has around 8.5 million of customers. Belgium produces 20 gigawatts and is around 11, 12 million of people. Colombia, the region I originally come from, produces 17 gigawatts and have around 51 million of people. So the energy per capita of Quebec is one of the highest in the world. It's per capita, it's very high. This is just some pictures of the reservoirs and specifically the research center. There is around 500 researchers, engineers, and technicians. We work in nanomaterials, we work in AI, we work in transmission distribution, we work in the client side, we work in cybersecurity, high performance computing, quantum computing, a lot of things. My unity of research specifically works with the clients. So we are the interface between the grid, the needs of the grid, and the client. So what can we do for the clients to improve their consumption, but how the clients can help also the utility. So that's specifically our job. Very happy to be members of the Linux Foundation Energy. It was a lot of work, but finally happened. And we check in the Linux Foundation Energy landscape, and there is not a project that addresses buildings and heating of the Linux Foundation Energy. There are a lot of other open source projects out there, but there is not one from the Linux Foundation Energy that specifically targets that. So maybe we can come with an idea to propose something for that specific area. We are aware, of course, of other leading projects as the Carbon Data Specification Consortium, and the Interconnect Initiative, also very interesting. But those projects, I feel, don't address the needs we have as utility of how to manage the assets of the customers. So I will just give like an overview of the problems that you will face when you want to connect the assets of the users behind the meter, okay? So TSOs, markets, DSOs, aggregators, customers, users, control systems, users, and devices, okay? So this is a landscape of what usually how it is the energy sector. So you have either one or multiple DSOs, you have either one or multiple aggregators. The DSOs either have direct contracts with the aggregators or they interchange information in some way. The aggregators go and talk to the control systems. The colors represent different protocols of communication. So the aggregators either use their own protocols, their own way to talk to the control systems. Sometimes the developers of the control systems are the aggregators itself, like Tesla, for example. They fabricate the control system and also make some kind of aggregation. And finally, you have the devices. So some controllers, they use proprietary protocols to talk to the devices. And some devices are fabricated by other people, and they use their own protocols as well. So the controller can be controlling devices that are their own, or can be controlling devices that are developed by other people. So when you go up in the chain, it's very easy, because everything is property of the power utility, or everything is property of the TSO. The assets are property of them. But as you start to go down in the edge, you will have a more fragmented system. And that's when you start to face the real challenges of how can actually we talk, understand, and control those devices to serve a purpose. So just here, there are some efforts, of course, of standardization of protocols. So for example, we have the IEEE 2030.5, we have the OpenADR 3.0 specification. And of course, what we need is a way to make the buildings an asset for the utility. The buildings itself need to become an asset. So we want connected buildings and interactive buildings, that they respond to the needs of the grid. And not only buildings, but all the assets that come with the building, HVAC systems, electric vehicles, whatever system is deployed, we need it to be interactive and respond to the needs of the grid. So even though there are some efforts, the status quo is very far from what we wish to be. So just a little bit more of detail in the connection between the DSO and the aggregator. Usually what you will do is that you will try to use a protocol between the DSO and the aggregator, and the brain is going to be on the aggregator. When I talk about the brain, I'm talking about the intelligence that is going to take decisions and coordinate the assets. So you will deploy the brain on the aggregator, and what usually happens is either the aggregator talks to the controller because they are compatible, or they talk directly to the devices, either because the aggregator owns the devices, as I say first, or because they make some integration with existing devices. So that's the way it's working now. But already, the buildings itself, they have control systems already there. There is someone that install a control system in the building, either a company that dedicates themselves to do that, and they use Johnson Controls, Siemens, they use Delta, they use Niagara, I don't know, all the big providers of control systems for the buildings. And they already have control logics installed there. So how, as a utility, can we enter in coexistence with the control system that already exists? We don't want to replace the control system because that's their job and they do it very good. We want to coexist with the control system and use it only when it's required for the utility. So that's one of the questions. So what you can do, or usually what aggregators, what they will do, is that they will put like some form of aggregation in the edge, like a protocol conversion, for example. And then they standardize the communication with the protocol conversion. They use proprietary solutions, or they use Azure, Amazon, AWS, whatever. So they use a standard communication bus until the protocol conversion system, and then the protocol conversion system go and converts to MQTT, converts to Zigbee, converts to REST, to whatever protocol is being used on the edge. So somehow kind of solve the problem of the protocol, but still it will be a messy system. So, and in the end, when you try to integrate the devices, some of them are property of the aggregator. Some of them will be integrated as third parties. Just like I want to put them inside of my bus of events. Like aggregator is a IoT manager. They manage IoT devices. So you can connect it like inside of your bus system of communication. You can also develop like an API, and then they will find a way to connect to your API. So for example, we make demand response events, and they connect and read that, but they develop their own control logic, and they connect to that. And finally, the devices that will maintain their own control on the cloud by themselves. So for example, if you try to control Google devices, you can control it with the API direct if you are the user, the end user. But if you are a utility, you need to go and pay a different API that is specifically dedicated for aggregation purposes. And then you need to go and pay for them in a different way. So these devices, you cannot integrate it easily. And when you are a utility, you need the response in the specific area, in the specific moment that you need it. And some of these, they don't allow that kind of granularity. They sell everything like a block, okay? So it's like not answering the needs of the utility. So this is what you face when you try to develop a control system that wants to integrate the devices that already exist on the system. And we work, I work here. So trying to answer the needs of those guys and trying to find out how to talk to those guys and control those guys. So it's very complex system. So what we say, and it's just a proposition, it's not, doesn't mean that needs to be that way. But it's one of the things that we say, okay, what if we put something on the edge, okay? Something on the edge. We can distribute the brain. Now, doesn't necessarily need to be on the aggregator or on the cloud. It could be on the edge. It can make the protocol conversion, or it can talk directly to the controller that already exists, okay? It can talk to the controller. So you can standardize this communication, OpenADR, EEE, whatever. You can standardize this communication to the edge, and then you force those guys to connect to this thing. So that's what we were discussing this morning. I don't see more alternatives, honestly. But if this is a Schneider and this is General Electric and this is Delta or Johnson Controls, and you have one device, a standard communication, you say you should connect to this device. First, you should allow data reading from your own system. That's complex already, because a lot of them don't want to share the data. And second, you will need to access to control the devices that they are already controlling for critical needs of the grid. There are some needs of the grid that doesn't critical. They can answer it somehow good, but sometimes you need something critical because a transformer is going to overpass the limit, or you have critical cases in which you need to guarantee that the response is the way you want it to be, okay? So, as I say, it's just a proposition. So we say, okay, if we develop this edge device, we standardize almost everything, and we ask the providers of the technology to connect and to interact with the edge device. That will allow utilities something that they cannot do today, which is reach the devices, read from them, and control them. It's not possible today, unless through an aggregator, okay? So that's basically our idea, to take the brain a little bit lower and put it on the edge part, not all. So which are the advantages? So you enable a standardization of communication in all these green areas, and it profits from existing controllers. So at least try to profit from existing controllers. Which are the disadvantages of that? That the integration with the existing controllers is complex. It's very complex, and a lot of people maybe will not want to do it. They simply will not want to do it. So in very big, high level, that's what we try to do with OSED. That's the open source EDGE DERMS. In very high level, that's what we try to do. We try to develop this entity here, the one that somehow controls the other controllers. We have, for the moment, very simple communication with DSO. We have very simple communication with the edge devices, and we find a way to integrate the edge devices with already existing controllers, like Home Assistant, like EdgeX, another project of Linux Foundation, and other types of controllers that you can leverage that already exist. So in very, very high level, that's what we did, and that's what we will try to present today. So you can have standardized communications in the edge, just until the edge. You can deploy custom grid functions. So this morning we were discussing that internet protocols are very widely used, and everyone agrees on that. And utilities somehow think that their problems are unique and that everyone needs to build their own solution. And that's why you have everyone doing the same, but in a different way. So if you have something standard, and then you can develop like custom grid functions on need, like, okay, at least we agree on these, but I need this specific, you just add it as a module, as an app, for example. That could be something good. And to try to somehow use what already exists on the system. So that's like the context, and if we can discuss now, we can discuss after if you have some questions. At least the idea, it's clear somehow, right? Yeah, okay, thank you, yeah.
Thank you, Juan. I will continue with the vision behind the OSED platform. And Juan will come after to present a small demo. So we can't be explain the vision behind this project without explain the idea behind this vision. I hope everyone know Phil Simon, this book. He described the platform aren't just product or service. They are ecosystem that allow others to create value. This is the main idea behind this project. And that's exactly the vision behind our open source EDGE DERMS. We are not just developing tools. We're creating an open and also vibrant playground where innovation happens at the edge. From local community to global enterprise, everyone can jump in and shape the future of energy management. So if we take this example, for example, the most powerful platforms are rooted in equally powerful technology and their intelligent usage. So, in other words, they differ from traditional platforms in that they are not predicated or particular physical asset land. For example, mobile applications that are developed like Facebook and others do not necessarily take into account the type of physical characteristic and of the camera or on the phone in which the application will be installed. So if you see the image, we want the same thing with the OSED. we want to be agnostic about the technology, about the device. We want something be capable to work in different cases. So our objective in this project is to, first of all, be cloud and hardware agnostic. So this is our first objective. And the second one is, when we talk about cloud agnostic, we want to work in Azure, in AWS, in IBM Cloud, and also Google Cloud and other one. And the other objective in this project is to add user technology in a modular way, so regardless of the manufacturer. So if you see, you have here coordination, you have graph, you have market, you have GDP, we have all that. We don't want to be, we want to add great function service, like all that function in a modular way. So after that, we want to deploy the system with geographic and temporal granularity. So substation, XFO, hours, etc. And we want the OSED platform be managed by a higher entity, like we call aggregator. So where are we? We are here. So EDGE DERMS, we are here, EDGE, function 1, function n, and all that function behind. So the OSED platform is already the deployment of a great function to make a day-ahead market coordination. We use this architecture for EDGE DERMS, and we are container. We are working deployment a give function to make direct control of the device, and we deploy the grid function that financially reward user to respond to the direct control signal. So I will let Juan continue with a small demo.
Yeah, sure. So this is some of the advancements made so far. We already deployed some grid functions. We already have the way to communicate those to the devices. And we already have some kind of intelligence on the buildings that are able to answer to the calls of the grid functions. This is the architecture of the edge. This is what we propose in the edge. So this is the intelligence itself of the building, okay? This is the actuator or the controller that already exists on the building. And in the end, you have the devices itself. So this actuator that already exists on the building could be Home Assistant, could be Home Assistant for residential, could be EdgeX from the Linux Foundation Edge, I think. Could be EdgeX, which work good for commercial and institutional buildings. And what we are starting to look now is that it could be also Johnson Controls, Delta, Niagara, as long as they allow us to read their data and to coexist with their control systems. And you need some layer of separation, and you need some way of abstraction to separate the intelligence from the actuator. If you want to control a thermostat and you want to optimize the consumption of electric vehicle, you don't need specifically to know which type of vehicle is. You don't need to know exactly which thermostat is. You need some simple information, which is the capacity of the battery, how much fast can I charge and discharge it, which are the limits that I can move, but that doesn't require to know if it's Zigbee or if it's Modbus or if it's BACnet. It doesn't require. So this abstraction allows us to develop the optimization algorithms as pure research, and after we handle the complexity of the protocol itself down. So this abstraction is what allows us, and this is the part of the edge. In the original image I was showing the edge, that's the intelligence. And how we connect to the system is the other part, okay? So this is the architecture that we propose in the edge. And now, the fun part. This is a photo of our lab, a picture of our lab. Hydro-Québec have multiple labs, but are mainly separated in two big campus. One is in Montreal, in Varennes. This one is in Shawinigan. This is the one I work in LTE. So because we work with the client, we have a lot of technologies for the clients. So we have a big institutional building in which you have batteries, we have these are electric panels, we have a charging station. In this picture it's not there, but it's already installed. We have an IoT lab specifically designed for IoT devices. We have some houses, 2 houses, they are twin houses. So the idea is that you can test a control system in one house and the other leave it as reference to see if it's effective or not. We have 2 small sheds that also have heating and cooling. And we have distributed generation. So this is the place we deploy the system. The sheds, they have sensible air, I think, something to control heat pumps. The houses, I think one has Sinope, which works with Zigbee. The other, I think there is a Kovi. We have the lab IoT, where also we have Sinope, which is Zigbee. And we have a battery, which is Modbus, and electric charger, which I think is Modbus also. So I work on the abstraction, and other colleagues work in the protocol, so I'm not too much good with the protocols, but that's what we have deployed there, okay? So we deploy a coordinator, one entity that coordinates with all the devices and exposes APIs for a higher entity that will consume those APIs. So in the first phase, we are not proposing to the coordinator to be intelligent by himself. We are proposing to expose APIs, and someone else more intelligent is going to take the decisions. So this is the connection to the Kubernetes server. That's why we say it's cloud agnostic. You can deploy it in every cloud that you want. So this is the coordinator that already exists there. And the internet don't want to, I think, yes. Somehow my internet, we are using the internet of the phone. Okay, I'll try to fix this. Okay, let's see if this works. First, the middleware that we are using now is ThingsBoard. I don't know if you are familiar with ThingsBoard. Yes? Okay. Okay. It's a lot of middlewares. The idea of the utility is not to manage the IoT devices itself. That's the work of the aggregator and someone else. The utility just needs to communicate with the devices itself. But we implemented a middleware, IoT middleware, because it's easier for us to manage the IoT fleet. So we have 2 sides. We have the LTE and we have the EQTR. The LTE is the lab, and here you can see like the buildings that we have there. We are using the IoT middleware just for communications. We have simply MQTT. Ideally, that should be OpenADR or something more standard. But for the moment, it's very simple. It's just for making tests. So it's MQTT. These are the measuring of some of the buildings. So this cabanon is one of the sheds that I was showing in the map. Yeah. So this small building here, it has only one thermal zone, and is this one. The other shed is exactly the same. It has one thermal zone. This is one of the houses. The internet is not good, no? It worked? Okay. So this is one of the houses. It has 6 thermal zones. You can see here the consumption of the building, the set points. Sorry. Yes. Let's check this one. Because if we don't have good internet connection, no. I will not be able to test. Okay, I think kind of working. Okay, so this is the measuring that is already now live on the buildings. So I will try one last time. No, I cannot. This one or the
This is the password.
Susan. Is sharing?
Yeah. Let me. It's connected. Try again. Try to open Google first. Try to open.
Because if I don't have connection to the server, I cannot deploy the grid functions, and we cannot see that nothing happens. No, this is a connection to our Kubernetes cluster that is in Amazon Web Services.
Web server.
It
is a web server.
Yes, this, yes. So what I'm trying to do is to access.
Opening the local host, meaning your computer.
I am trying to access the server on the cloud and forwarding a port to my local computer.
Okay.
I think it's this what is failing, this tunnel.
The connection.
The root URL worked.
Come on.
The root URL when you forward worked, but when you went to the documentation, then
It seems, yeah, but no, it seems that this connection, even this one, is not because it's like it's unstable, maybe. So that's the forward port. It says it was forward, and then. I think it's just the internet is failing. So this is few of the grid functions that we have, like coordination for the next day, optimization for dynamic tariffs. So we send a dynamic tariff, and the edge systems optimize for the day ahead, for the next day. This is control of direct control. It's just examples to show that something that you can do. And this one is interesting. It's using blockchain, how to pay the users for doing an action, a control action. I will try this one because it's simple, and so if I send here, for example, I don't know, 18, hopefully, if it's still working, and here on the cloud, I should be able to see. Okay, yeah, so it broadcasts to the users, it finds some users, successfully sent the request, and here is saying that they were successfully modified on these buildings. So in theory, if I go to this, I should start to see that the set points start to change to 18. So if I go here, okay, already changed, and the no, already changed, and this one is slowly changing. So this is, for example, to test the direct control itself. We can do it with batteries, we can do it with electric vehicles, it doesn't matter. It's just to show. So that's actually the idea. We have different types of grid functions. This one is direct control. If you want to do it, you can do it. If you want to pay the users, we can try that one after. You can do it. If you want, for example, to send a tariff for the next day or for a period of the day, like time of use or these kind of tariffs, you can send it, and the system, the edge will receive the tariff, will optimize the devices that it has, and will create a profile optimized for the next day. And this one is the more complex one. This one is, what if you have like a lot of electric vehicles, for example, and you want to coordinate them. You want to make a coordination. So let's say you have enough energy, but you don't have enough capacity on that transformer or at that level. So you can say, I will charge first this block of vehicles, after I will charge this another block, and after I will charge this another block. And the good thing of the edge is that you can know the needs of the users on the edge. For example, for the control of the thermostats, they learn the thermal preferences of the user. So they know that I like 18 degrees on my room. And they know that other person likes 20 degrees in another room. So they use machine learning to learn these kind of things, to learn the schedules of use of the electric vehicles, to learn the usage. And all this information is private. You keep it on the edge. The utility doesn't need to know that. Why the utility needs to know the status of, I don't know, something. So we keep it on the edge. And if it's critical information, like big loads or things like that, you can choose to send it to the cloud. So that's another good thing about the edge. Let's see if this is still working. We can make another try. I just want to see if this is still working. And let's check here. So, yes, it's not, yeah, I have one, yes. Okay, I don't know if this is working. No, this is old. Okay, this one is 18. No, this is the old. Yeah, it seems the connection was lost. Let's try again. Let's try this one. 20. Then 22. Okay, execute. And I am not sure if I have this. Yes. So this one is the one that uses the blockchain to make the payments. So you can create wallets for each user, and then you just use whatever protocol APIs and make the payments, and the users will be paid. And this is interesting for markets because the users have the option to answer how much they want to charge. So the utility say, I need this grid function, I need to do this, how much you will charge, and the user can decide the price, and then the utility can decide if it's going to pay or not. So the idea is if you're going to make curtailment or you're going to reduce the consumption, you want to do it with the cheapest kilowatts available. So instead of just picking a fixed tariff, you just pay whatever is the cheapest prices, and then you have the flexibility you want at the cheapest price that you want. So I just want to verify the logs of the coordinator, if it did something or not. Okay, so it says that it sent the request after the users answer with the invoice of how much they are going to charge. Then it pays the invoice, and after it sends the confirmation of the payment, like I already pay you, so execute the grid function. And then the users apply the grid function itself. So if I look at the manager here, so this is what originally you have, like 9,134, 123. So yeah. So I can refresh these. In theory, these numbers should have changed because this is the wallet paying the others. So hopefully, yeah. So now you have 9,000, and they have different, whatever they charge for deploying that grid function. This is because we started with transactive energy, and the idea was to deploy a market. So we developed this, but after we add other grid functions. So I don't know how we are the time, but we can just like wrap up, and maybe if people have some questions. But the idea is that to deploy a system on the edge, which is the DERMS EDGE Coordinator that we deploy a system on the devices, on the buildings itself. I think this one summarizes everything. Deploy the edge devices and communicate with the existing controllers and make the control. And this coordinator, you can deploy it when you need it and where you need it, only to do the control actions that you need. And this coordinator for the moment is not smart. It answers the calls of other smarter higher up, but we can develop intelligence for him as well. So imagine, for example, a transformer that overpassed its capacity. You use OpenOIDR, and automatically he feels that he's overpassing the capacity, so he triggers the demand response himself. Yeah, so I don't know how we are on time. We have? I still have?
Presentation has to start right now.
Right now? Okay, so there is no time. Okay, yeah, well, thank you very much.